In the last clip, we were introduced to this DT graph, and we know that the velocity is the slope on a DT graph. Um, this velocity is constant. We know that for a couple of reasons. The first one is, in the problem that I used to set this up, I explicitly stated the velocity of the vehicle was constant. In the other instance, the slope is constant, and the slope is the velocity. So if the velocity is constant, then by definition there is no change in the velocity, which means the acceleration is zero. This object is neither speeding up or slowing down. But just a quick note on this, if we were to look at a velocity time graph, or excuse me, a displacement time graph, under the same circumstances where we were moving from x naught to x and in some elapsed time from t naught to t, then if the object were moving in the positive direction with positive acceleration, then its rate of travel would be increasing. And since the slope is that rate of travel, the velocity, that slope would be increasing. So it's interesting to note, and will be useful to us later, that if this graph curved upwards, this, in fact, any curve on a displacement time graph means acceleration. So let's remember that. The first one, let's definitely remember that the slope is the velocity. The second one is that a curve means acceleration. Right? Straight line is constant velocity. A curve is acceleration. If we're moving in the positive direction, and we have positive acceleration, this curve is upwards. Conversely, under the same circumstances, if we are moving at some velocity in the positive direction, but we have negative acceleration, we will be slowing down. Velocity will be decreasing, and so the slope will be decreasing. So this would be an example of positive velocity with negative acceleration. That will probably be all we need for the DT graphs at this time. And we're going to come back and hit these hard. We're just getting an introduction to them now. But let's look at a different situation. Now let's take a vehicle that is moving to the right at, with a constant acceleration. So the initial velocity is 0, and then 1 second later it is greater than 0, and a second after that it is greater still. So if it has acceleration, by definition its velocity is changing. So in this case, as with all cases in this class, the acceleration is constant. So when we look at a graph of this car's velocity over time, we know at time 0 the car has 0 velocity. That's a given. So on our graph, if we're graphing velocity versus time, this is let's just call this a VT graph because brevity is awesome. So on this VT graph, velocity time graph, the velocity is not constant. The acceleration is, which means the change in the velocity is constant. And if that rate of change is constant, then for every second that the car moves, every second it will increase by an equal amount in velocity. That's because the change in the velocity is constant. So the rate of change is constant. This gives us our straight line, and ought to be a really big hint as to what exactly the slope of a VT graph tells us. So the slope, we know, is rise over run. In this particular case, any change in the vertical axis is a change in velocity. Any change in the horizontal axis is a change in time. So the slope is the change in velocity over time, which we know defines average acceleration. Since our accelerations are constant, let's just say it defines acceleration. So on a VT graph, we should definitely know that the slope is the acceleration. But something else pops out of this VT graph that's pretty useful. If I were to solve for the area under this graph, that's actually going to tell me the displacement of this object. Um, and now let's figure out why, guys. If I it's easiest to see with a constant velocity over time. So if I had velocity over time and the velocity didn't change and it was constant, then the area under this line is actually V times T. We know that V is delta X over delta T. Therefore, delta X, the displacement, is V average delta T, which is the area under this line. So the area gives us displacement. And these two things are definitely worth remembering. One last little item to note here with this velocity time graph. If the rate of change is constant, meaning the acceleration is constant, then on a VT graph, which is linear with constant acceleration, you can see that the average velocity, which we know is the displacement over the time, it's also actually the average of the initial and final velocities. V plus V naught over 2. Now, this is only valid with constant acceleration. But if you look at it, the area under this triangle here that I've shaded is the average velocity here. There's the average. So with the constant change in velocity, since it changes at the same rate in any period of time, the average velocity is just the average of the initial and final velocities. This, guys, is going to be another equation of motion. It's worth remembering that V average is V plus V naught over 2. This is useful and worth memorizing, so know this. Remember, use your brain.